All right, we've been talking about spontaneous reactions have a positive cell potential. We can relate the cell potential to delta G and to K using the equations here in this little diagram. So for a spontaneous reaction, our delta G value needs to be negative. Remember, we learned that back in chapter 17. Our cell potential needs to be positive, and our K value needs to be greater than 1. Greater than 1, so our reaction will lie to the product side. We already learned about relating delta G to K. Delta G under standard conditions is negative RT natural log of K. And delta G can also be related to our cell potential. It's negative NF times the cell potential. N is the number of electrons transferred. And then F is Faraday's constant, 96,485 coulombs per mole of electrons. So let's work through using these kinds of equations. So calculate delta G for this reaction at 25 degrees Celsius under standard conditions. So we're looking at our IO3 minus, so this, and I minus going to I2, so this reaction. So we need to find our cell potential is going to be 1.20 plus negative 0.54. I'm flipping that one. So that gets me a cell potential of 0.66 volts. Then if we go back a slide, we can find the fact that our delta G under standard conditions is negative N times F times our cell potential. Our Faraday's constant, again on the previous slide, is 96485 coulombs per mole of electrons. Then we have to figure out how many electrons were transferred. So we've multiplied this reaction by 2. We're transferring 5 electrons there. We multiplied, or we can look at our other equation here that we multiplied. Where's my I minus? I have 10 I minus, so I multiplied it by 5. So again, I'm transferring 10 electrons. So my delta G is going to be negative 10 times 96,485 coulombs per mole times my cell potential, which is positive 0.66 volts, and volts is joules per coulomb. So I can calculate my delta G under standard conditions is negative 6.37 times 10 to the 5th joules. Because I end up with my coulombs cancel, my moles cancel, so I end up in joules. Now, note you will always be given this equation, Faraday's constant. You don't have to memorize those. So negative 6.4 times 10 to the 5th joules. Makes sense. Next, calculate K for the reaction. Copper plus 2 hydrogen goes to H2 plus copper 2 plus. Now my copper, I have to look up in my table, my E naught for copper is, so copper going to copper 2. So for copper 2 going to, plus 2 electrons, going to copper solid, is 0.34 volts. So I'm going to reverse that. Oh, and then this H plus and H2 is just the standard hydrogen. So my cell potential is going to be negative 0.34 volts because this reaction's reversed, so I changed the sign. Then from a couple slides back, I can use my Nernst equation, which says Ecell is equal to 0.052592 volts divided by N, my number of electrons, log of K. My number of electrons is 2, and my cell potential is negative 0.34. So if I take negative 0.34 times 2 over 0.0592 is equal to the log of K, then I can find that K is equal to 3.26 times 10 to the minus 12th. It makes sense that K is very small because my cell potential is negative, so my equilibrium is going to lie very far to the reactant side because it's not spontaneous in the forward direction. One more example here, calculate delta G for the reaction. Again, we have to look up our values in our table 18.1. So my reaction of iodine, I2 plus 2 electrons goes to 2I minus. My cell potential is, potential is 0.54. Then my potential for bromine plus 2 electrons going to 2 Br minus is 1.09, so reverse, negative 1.09. So my overall cell potential is 0.54 minus 1.09, which is negative 0.55. Then I can use my equation where my delta G is equal to negative NF cell potential. So my delta G is, I'm moving 2 electrons, so negative 2 times Faraday's constant, which was 96,485 coulombs per mole, and then times my cell potential, negative 0.55. So my delta G naught is 1.06 times 10 to the 5th joules. So I am not spontaneous because that's positive, which makes sense because my E is negative. We're not spontaneous in the forward direction under standard conditions. One more practice. Again, I would recommend pausing and checking this. Here we have the reduction potentials on the slide, which is helpful. So we're looking at this one and this one again, which gets us our cell potential. We've looked at this reaction a couple times, is 0.66. Then my equation, my cell potential is 0.0592 volts over my number of electrons times the log of K. I didn't talk about that 0.0592 volts. That comes from combining R, the temperature, and Faraday's constant, and then switching from natural log to regular log. So it's combining a bunch of stuff together. Anyway, 0.66 is equal to 0.0592 divided by my number of electrons from the last time we did this was 10, because we have a 2 here and 5 electrons, so divided by 10 log K. So then I can solve for K, and I actually get, so if you take 0.66 times 10 divided by 0.0592, you get the number 110. Sorry, that's log K, which means that K is equal to 10 to the 110th power, which my calculator cannot do. So that's a very big number for K. Equilibrium is going to lie very far to the right.